Though most people associate Hooke's law with springs, it actually can be used in many situations. Anytime you have a force that works against an object's motion in a linear way, in a proportional way, then the ideas that we're talking about in this section will hold true. But the idea of a mass on a spring is an easy one to visualize, and so we use this as a model for a lot of other situations. This formula here is again referred to as Hooke's law. F sub s is the symbol we use for the force that the spring is exerting. Delta x is how far the spring is being pushed or pulled compared to what its equilibrium point is, where it's naturally relaxed. And K is something called the spring constant, which we'll talk about in just a few minutes. Something that's important to recognize is that the spring force is always trying to pull things back to the center, always trying to pull things back to equilibrium. And so F sub s is often called a restoring force. It's trying to restore things back to equilibrium. So again, K is called the spring constant or sometimes the force constant. And if we used our standard units for force and delta x, we would expect K to be measured in newtons per meter. Notice not Newton meters like we used for torque, but newtons per meter, the proportionality constant between the force and the distance stretched. K is a value that represents how stiff a spring is, how difficult it is to stretch or compress it. And so springs in like a shock of a car are going to have very high values in the thousands or tens of thousands, whereas the springs we use in our class will have values that are, maybe only 10 or 50. Something that is smaller, they're bouncier, they're looser. Even though there's a negative sign in this formula, that negative sign refers to the direction between the force of the spring and the displacement. The value of K should always be a positive number. To determine K, we often look at an equilibrium situation, a situation where a force is somehow being applied to a system involving a spring, and then everything's allowed to come to equilibrium where the forces are balanced. And in this way, we can determine what the spring force is based on the applied force. A typical experiment would be suspending a spring like this is showing here, hanging from a horizontal support and looking to see where the end of that spring lies, and then placing a known mass from the bottom of the spring so that it is pulled, it's stretched, and then measuring how far that stretch is. And then by taking the force that the weight applies divided by the amount of stretch, you can determine K. A better method, of course, is to use a graph. And so a lot of times the information about spring constants is given as a graph. And so you need to recognize that the slope of this would tell us the value of the spring constant in newtons per meter. Later in this unit, we will be using this idea to determine the equilibrium point for a system, and then we'll disturb the system and allow it to oscillate. So this process of determining the equilibrium point or determining K using equilibrium will be important later.